Hawking effect and radiation are same or different?
Hawking effect is the emission of radiation that we call Hawking radiation. So are we ready? Okay. So as we said before anything, no class Thursday, no class following Tuesday. So we will see each other in a week from now. So this chapter goes about the Hawking effect, and let me start with a brief introduction before going to the details. So as you know, the Hawking effect is probably the most celebrated, or one of the most celebrated predictions of quantum field theory called spacetime. It was derived by Hawking in a single operator in 1974. 74 he wrote an Nature article describing in general what happened, and in 75 he wrote a much more detailed paper with all the computations. And in short, what Hawking told us is that once quantum mechanics appear into the game, essentially black holes are no longer black. This idea that black holes are completely black goes away. Rather than that, they are surrounded in an avoidable way by they emit so they become surrounded by outgoing thermal radiation. Radiation, I mean, when observed from far away. This is quite an astonishing prediction, black holes. Now, once you put H bar in the theory, they see as emitting thermal radiation of all fields that you can imagine, the scalar fields, electrons, positrons, neutrinos, photons, whatever you can imagine. And as I said, from far away, that radiation is thermal. And this, as you can imagine, has really far-reaching consequences. Just to mention a few of them. So first, black holes are not eternal anymore. In general relativity, black holes, they can do is to absorb mass and energy and grow in mass. Now, that is no longer true. Black holes can emit radiation. That radiation will make them to lose mass in the evaporation process, and eventually they could completely disappear. So that is a radical change in our way of understanding black holes. Second, this establishes a deep relation between thermodynamics and black hole physics. First of all, a temperature and entropy can be associated with the black hole. So we can define the temperature, the thermodynamical temperature of a black hole and the thermodynamical entropy of a black hole. And even more, one can, as we will see in some detail, one can really apply all the laws of thermodynamics to systems contained in a black hole. That is not possible in the classical theory, and we will explain why. In the quantum theory, that will be possible. Another consequence is that a whole new family of conceptual problems appear. Just to mention a few of them, as I'm sure you have heard, we have the possibility of having a breakdown of unitarity in the time evolution of the quantum field theory, in the time evolution of QFT. That it is possible that in the presence of a black hole, time evolution is not implemented by a unitary operator. It's not a unitary transformation. Therefore, information can be lost. So this is what people call the information loss paradox. Another conceptual problem is, what is the nature of the microscopic degrees of freedom giving rise to this entropy and temperature, producing or behind the temperature and entropy. We know from statistical mechanics that entropy, temperature, all these thermodynamical quantities are just averages over microscopic fundamental degrees of freedom. If now really thermodynamics applies to a black hole, what are those microscopic degrees of freedom? Probably they have to do with quantum gravity, but now now that question is in front of us and we should answer that. More questions there are. I could continue for the whole afternoon. So what is the fate of the singularity, of the black hole singularity at the end of the evaporation process? Etc., etc., etc. Maybe something really remarkable is that 40 years after Hawking discovery, all these questions are on the table. People are actually discussing all this quite lively. So my opinion is that we still have big challenges in front of us regarding black hole physics and quantum mechanics, and this makes this a really fascinating field.
Ivan,
Go ahead.
can you write slightly bigger?
Thank you.
Okay, thanks.
Okay, so in this chapter, my goal is to summarize Hawking original derivation and posterior developments. So giving you a global picture of Hawking radiation and where all these issues appear. A Hawking, with Hawking radiation itself, that deserves a whole course. One could just have a course entirely on Hawking radiation. So the best I can do here in 5 or 4 lectures is to summarize it and summarize the main features. So this is not a course only on Hawking radiation. So if you really want to have more information, there is plenty of literature. Again, my goal here is just giving you a summary of the main things. If you want to know more about it, good references are the following. So something that I find pedagogical is the book of is in the references that I gave to you, the book of Fabry and Navarro Salas. That is a book on just black hole elaboration, so Hawking radiation. So that has a lot of information about the classical and the quantum theory. If you want something more rigorous, you go to Wald's book on QFT. Also, in the GR book has a lot of classical black holes, so you can complement that. And any book on quantum field theory, on any review of quantum field theory in course of spacetime has a section or a chapter on the Hawking effect. So you can go to those references to complement what I'm going to say, because I insist I will just summarize the main features. So the plan of the chapter is the following. At least the first section. I want to start, because some of you didn't have the GR course yet, maybe are not very familiar with the geometry of black holes. I want to summarize for you the classical preliminaries. So what is black hole geometry, and the Penrose diagram of a black hole that they will use a lot in deriving Hawking effect, and also summarizing these thermodynamical properties of classical. So what classically GR tell us about the thermodynamics of black holes. And then I will go to the QFT in section 2, just deriving Hawking derivation. I will do this in a very simple scenario. So the simplest black hole that you can imagine, that was described by Javi this morning in his talk, which is just a sphere, a spherical shell of radiation collapsing, spherical shell of light collapsing to form a black hole. That is the cleanest scenario. And in the section 3, I will generalize the result for more generic situations. And I will have more sections that I don't know how long this will take me, so I will write the rest of the sections on the course. Because what happens always is that you start writing notes and you realize, wow, this takes 2 months to explain what I want. So because the Hawking effect is so rich and it has so many things around it that depending how I go at the beginning, I will cut it in different ways. So let's go to classical preliminaries. So this section by itself has 3 subsections. Schwarzschild metric, for those who have never seen it. So this section may be boring for people who are more familiar with this, but it's good to go over that. Then Penrose diagram of a black hole formed by gravitational collapse. And 1.3, I will describe black holes thermodynamics. So let me start with section 1.1. So as you probably have heard before, in 1916, Karl Schwarzschild wrote the first exact solution to Einstein equations. This was really remarkable. Just a few months after, I think it was February, Einstein published GR in November. So just a few months after Einstein wrote. And even Einstein himself was extremely surprised to see that one can find exact solutions. He saw that the equations were so complicated that finding exact solutions would be difficult. A few months later, this guy, I think he was 19 years old, or he was quite young, and obtained the first solution. He was in the middle of the war. He died 1 year after. So quite a big loss. So the solution describes the geometry outside. So there are 2 words important here: outside of a spherical symmetric body. Spherically symmetric body. So important word outside, because really this is a vacuum solution. So when the solution applies, there is no matter. Matter is in the star, and the metric doesn't describe the interior of the star. And second, spherical symmetric. So vacuum and spherical symmetry. Body of mass m. The total mass of the body is m. And this metric in some appropriate system of coordinates that define really the metric is the famous Schwarzschild metric, 1 minus Rs over R dt squared plus 1 over 1 minus Rs dr squared plus R. This capital omega is just the standard two-sphere. So you can see the metric is spherically symmetric. There is no theta and phi in any of the metric components. And this is the Schwarzschild solution, where Rs is a constant. It's called Schwarzschild radius, and in units in which c is equal 1 is just given by this. So Schwarzschild radius. It's spherically symmetric, but also note that the coefficients doesn't depend on time. So this vector field is also a Killing vector field. So the metric, at least for outside the Hubble, the Schwarzschild radius is stationary. So this is what we call a stationary black hole. All of you have seen this metric before. And the main feature always is, is that note, I want to give a number here. Let me call this equation 1. And the statement is that, note that 1 is singular at radius equal to Schwarzschild radius. When the R coordinate equals this constant, Rs, the metric is singular. In particular, you can see that the determinant, this diverges, this is 0, so the determinant is ill-defined, the metric becomes degenerate. So G mu nu is degenerate. And the question that we want to ask here, as usual in GR, is the following. Is this singularity a real physical problem with the physics, or is just a bad choice of coordinates? Is an artifact of our coordinates, or is a real physical singularity? So, real or coordinate artifact? That is the question mark. If you want, as an example, consider the metric of the Euclidean plane in spherical coordinates. The metric of the Euclidean plane in spherical coordinates is just dr squared plus r squared d theta squared. This metric, if you put r equals 0, you find that the determinant of the metric is 0, and the metric has to be invertible. So this metric becomes degenerate at r equals 0. So would you say that that is a physical singularity? So no, there is nothing wrong in the plane. In fact, I can choose the origin wherever I want. That point is just, that apparent singularity is just a coordinate artifact, that my system of coordinates is not valid anymore at r equals 0. So example, so is degenerate at r equals 0. But we know that there is a coordinate singularity which has no physical relevance. So something similar may happen with the Schwarzschild metric, and that is the question that we want to address. It is a highly non-trivial question, and in fact, the physics of the Schwarzschild solution at r equal rs confused people, including Eddington, Einstein, everybody in the relativistic community for 40 years. You know, it wasn't until 1960 that people understood the physics of that. So it's not trivial at all. And you know, and the difficulty, this mixture between physics and coordinates is all around us in physics, but in GR is even more pronounced. And you know, in particular, you know, Schwarzschild gives you define the metric using coordinates. So extracting if a problem is coming from coordinates or not is highly non-trivial. And I mean, just as with some information, in GR, it's really difficult to know if a singularity is a real, if an apparent singularity is real or not. In fact, even today, there is no unambiguous method in GR of differentiating between physical and apparent singularities. There is the closest thing that we have is this geodesic incompleteness that Penrose, Hawking himself, and Gerosh introduced to prove the singularity theorems, but that is not unambiguous, completely unambiguous. So we really don't have any mathematically precise and ambiguous systematic way of detecting physical singularities versus coordinate singularities. So as I said, the best we can do is this. The best tool that we have is this notion of geodesic. I'm not going to explain this, just to tell you what it is. Geodesic incompleteness. And again, it was used by Penrose, Hawking, and Gerosh to prove the singularity theorems. And I mean, it is not difficult. You can find the derivation in any GR book, like in the Walls book. That, you know, why once these techniques are applied to the Schwarzschild geometry, one realizes that you know that R equal RS is really a coordinate singularity. The statement is that the system of coordinates we are using is just breaks down there. This system of coordinates is unable, you know, to coordinatize the whole spacetime. It breaks down. This is stuff that, you know, that the coordinate system is unable to coordinatize a manifold. That is very familiar to any student who has seen a course on geometry. Take the sphere, take, you know, polar coordinates in the sphere. The North Pole is always singular for a reason similar to that. The North Pole is where the angle theta takes pi. There is a sine of theta in the spherical coordinates. You know, there is a sine of theta. It is always theta squared plus sine theta squared d phi. If this becomes 0, the metric becomes degenerate. So the North Pole is always degenerate, and that means that, you know, coordinates, polar coordinates, are able to cover the whole manifold except, you know, the poles. And in fact, it's very well known that there is a single system of reference, single coordinate system, which is able to cover the whole sphere. You cannot find a single chart, a single coordinate system covering the sphere. So this is exactly what happens, or similar to what happens here in the Schwarzschild geometry. The geometry is not flat, the geometry is non-trivial, and you know, the system of coordinates, which is quite natural, far away from the black hole, is unable to cover the geometry beyond the Schwarzschild radius. And just historically, the problem, you know, the understanding of all these features was clarified when people found other system of references going beyond the Schwarzschild radius. Other coordinate systems well behaved across the Schwarzschild radius. There are many of them. Some of them were already written really early that people didn't realize or didn't appreciate. I think historically the first one was by Pain-Levé in 1921. And Gulstar, we now know them as Pain-Levé-Gulstrand coordinates. Just 1 year of difference, but people, these results didn't really impact the community, and it was really the work of Finkelstein in 1958 and Kruskal with the so-called Kruskal extension in 1960. Some rumors say that the Kruskal paper was written by Wheeler, not by Kruskal, who knows. And with Finkelstein and Kruskal is when people really realized, fully understood that was a coordinate singularity. So what I want to now is to summarize for you what Finkelstein did in 1958. So Finkelstein started defining some new coordinates. He called them small u and small v. I will try to differentiate because they are quite similar. By means of null geodesics. So these u and v are really going to label different null rays in Schwarzschild geometry. So first of all, let me write for you what are the null geodesics, and then define that for you. So in Schwarzschild geometry, null radial geodesics satisfy. A null geodesic is something that has line element equals 0, so they are going to satisfy minus 1 minus r pt squared dr squared equals 0. So I am writing this equation explicitly because one uses therefore, null geodesics satisfy that dt is equal to dr over 1 minus rs over r. And we use this to define a new coordinate normally called r star, where r star is what we call the Grech-Wheeler or tortoise coordinate. And from here you can check that this r star is just r plus Schwarzschild radius r minus Schwarzschild radius over Schwarzschild. And if you have never seen this before, I ask you to check that this is true. I am just defining this r. So the only thing you have to do is to take the differential and see that the differential is equal to this part. So just a trivial exercise. And it's just a more convenient coordinate than r because, you know, when r goes to infinity, this r star goes to infinity. That when r goes to the Schwarzschild radius, that coordinate goes to minus infinity. So this coordinate, you know, goes from minus infinity to infinity outside the Schwarzschild radius. Just to tell you that this r star is the analog of the coordinate zeta in real-linear spacetime. So you go to your notes, see the zeta coordinate we were using in real-linear spacetime, this r is the analog. Remember there, we started with rho, and we changed to zeta in such a way that rho was the exponential of zeta. So this is the same relation, a logarithm for an exponential in the image. Okay, so we have this r star. Let me call this equation 2. I forget to give it a name. And with this r star, we know that from 2 that null geodesics satisfy that d t this is really a plus minus, sorry. D plus minus r star is equal 0. This is a null radial geodesic. So now null geodesics are the set of points satisfying that. Therefore, so from here we can define what we are looking for. Coordinate u as t minus r star, the coordinate v as t plus r star, and from here easily we can see that along null geodesics u or v are just constant, because a null geodesic is d, u, or dv equal constant. So u labels outgoing radial null geodesics. So a geodesic and outgoing means that, you know, if we have this spherical symmetric star, light going away from it are in trajectories in which u is a constant. How do you know that it's outgoing and not incoming?
Because as r increases, t increases.
Right, because to keep u constant, when r increases, when t increases, r has to increase. So in time, that guy has to propagate far away from there. And this v just labels ingoing null geodesics. So we can define these new two coordinates just using a grid of null geodesics. So, you know, the contribution of Finkelstein was to realize that the problem with the standard coordinates, with t, r, theta, and phi, was in the t variable. That was his, maybe the key input, to realize that what is problematic in the initial coordinates is the t variable. So, and he replace it by v. So he wrote a new system of coordinates in which t is just replaced by v. This is what we call ingoing or advanced Eddington Finkelstein coordinates. Simple, just replace t by v, and Schwarzschild metric becomes in those coordinates are as d squared plus 2 dr dv. So now there is a non-diagonal term, dr dv. The metric is not diagonal anymore. R squared, the metric, the 2 sphere. Can any of you guess why this is nicer than before? We still have this guy that becomes 0.
You don't have denominator.
But not only that. You can check,
It's got another term in the determinant.
right, out of the diagonal. So if you
Ah.
compute the determinant, that is non-zero. So the determinant is different from 0 at the Schwarzschild radius, thanks to the non-diagonal term. Non-diagonal term, dr dv. So this metric, this different system of coordinates, this is what Javi in this morning seminar was calling horizon penetrating coordinates. So these are coordinates that go across the Schwarzschild radius and nothing happens. So this clearly shows that there is nothing singular with physics. Nothing singular in the physics of R equal RS surface. So physics is perfectly fine across the Schwarzschild radius. But is that okay? But non-singular doesn't mean boring at all. And in particular, the physical properties of the space-time metric across that surface are quite interesting. So, nevertheless, physical properties of the space-time metric of the space-time are very interesting around R equal RS, Schwarzschild radius. So to see that, just in a simple way, just consider an outgoing, again, null radial geodesic. So that means U equal constant. That is what happens in outgoing radial null geodesics. Or what is the same, du equals 0. And also you can check that dv grows. So the differential v along outgoing null geodesic will grow. Essentially because v is t plus r. If both t and r grow, v is growing. So then from from the new form of Schwarzschild metric in advanced Eddington-Finkelstein coordinates. For that null geodesic, ds is equal 0, because we are talking about light, and is radial, so the angle disappears. So what we have is that 1 minus v squared plus 2 dr dv, that must be equal 0. And dv is positive. So let's see what consequences we can extract from here. So first, pay attention to the region in which we are outside the Schwarzschild radius. You know, if we are outside the Schwarzschild radius, this factor, 1 minus this factor, you know, this is smaller than 1, this is positive, this is negative. Let me call this equation 4. So if this is negative and dv is positive, dr must be positive. So using 4, we obtain that dr must be positive. And this is what we expect. We have light outgoing, so you know it goes to increasing radius. R will increase. Surprisingly, the situation is very different if R is smaller than Schwarzschild radius. For R smaller than the Schwarzschild radius, this factor changes sign, so this factor becomes positive. Therefore, equation 4, which is true everywhere, tells us that dr must be negative. The conclusion is quite strong. Is that inside the Schwarzschild radius, even outgoing light evolves towards decreasing radius. So this tells us when we are inside the Schwarzschild radius, outgoing, radial light or any radiation, any null geodesic, goes towards decreasing R. Therefore, null geodesics can never escape from R equal to, can never escape the R equal or smaller than or equal region. And you know, I am considering the fastest propagation, which is outgoing null radial geodesic. Any other time-like or null geodesic will suffer the same fate. So true, this is true for any other time-like or null geodesic. So this is what we call a black hole, as you know very well. But it's remarkable that with this simple argument you can see those properties. So So if you want, let me say it better. So the region R smaller than RS is what we call a black hole, and R equal to RS is what we call the event horizon, which is the boundary of the region from which causal propagation can reach infinity. Just for completeness, let me make this diagram that most of you have seen many times. Time going vertically, R going horizontally. We have a star collapsing. So this is R equals 0. A star collapses. This is the surface of a star. A singularity, as I will say in a second, is formed. This wiggle line is always singularity, space-time singularity, as we mentioned. Event horizon starts forming, something like this. So this is R equal Schwarzschild radius, this point. This is what we call the event horizon. And as you have seen many times, if you start writing light cones at different parts of the spacetime, this light cone will be like this, symmetric. This is V equal constant, incoming light cone, constant. This line is U equal constant, outgoing light. The same for any other light cone. So this part is almost the same, but the outgoing one, when you get closer to the black hole, is getting more and more vertical until it becomes completely vertical. So at the horizon, even outgoing light is not fast enough to escape from the black hole, and inside the horizon, both outgoing or incoming lights will end at R equals 0.
I have a question about the detail of how that's drawn. So
It's smaller because I am a very bad artist.
No, the way the event horizon forms. Is it going straight up when it hits the surface of the star?
Here,
Yeah,
quite quickly, because
quite quickly, but not immediately.
nothing is immediate. So
Okay. I just
so this
wasn't
is
sure if
only
that's-
45 degrees, but in this region, 45 degrees is distorted, and here is vertical.
Okay.
I mean, what people really we could give much more details, but so I just telling you the minimum thing that we need to know. This blue shadow region is what Schwarzschild metric covers. Describes. So it doesn't describe the geometry inside the star. So geometry inside the star is not covered by Schwarzschild metric because, as I said, it's vacuum, spherically symmetric solution. So, just one more thing. Contrary to R equal RS, R equals 0, as you know, is a real physical singularity. You can characterize in many ways. Geodesics are inextendable, or curvature invariants blow up. For example, you can compute this Kretschmann curvature invariant, which is just contracting the Riemann tensor with itself. This is a scalar, so the value should be the same in any system of coordinates. And this is, I think it's 48. There is no pi, unless I forgot. 48 mass square over radius to the 6th power. This blows up when radius goes to 0. This is what we call a real physical singularity. The statement is that the GR breaks down in that region. This is not a surprise. We expect that when curvature, or any curvature invariant, gets of the order of the Planck scale, we expect the quantum aspects of gravity to be essential, and GR is a classical theory, so we shouldn't trust GR, in the region close to the singularity where curvature is of the Planck order. So, one has to insist that this singularity is not any prediction of the theory. It's just, a result of a theory which is not applicable. You cannot trust what GR is telling to you there. So again, this singularity is not physical. I mean, it's not a prediction in any sense. It's just signals that we need a theory of quantum gravity, and I expect that quantum gravity will make this region just non-singular. Probably quantum, completely quantum, space-time geometry will be quantum in the more quantum sense, but not in singular. Any questions for those of you who have never seen GR or this solution before?
Why does the event horizon grow at 45 degree there?
Here, because here the curvature is quite small, so really far away, light curvature is small, so light travels at 45 degrees. Here, if there is no too much mass, which has you have a star which is big in the center, the curvature is very small, so it starts to collapse. So it's expected that that region, the horizon starts growing. I mean, it's not exactly 45 degrees. It has some. It's really a time-like curve, but starts like this and goes to an hour, goes from 45 degrees to an hour, depending how fast it goes. For me, this region is quite amazing because here the star hasn't collapsed yet, and at this time there is already a horizon. So it's like if you are inside a star, everything is fine, but the star is going to collapse in a few weeks, but I have already a horizon. The star is collapsing, and that means that if I start running now as fast as possible, at the time where the star collapses, I will not be out of the region. So a horizon would be forming in this room right now, and that's perfectly possible. You will see that in this example, because there is matter, one is confused. But in the example of the collapsing shell, a very thin shell of radiation collapsing from infinity spherically to form a black hole. Inside the shell there is no matter, so you're in Minkowski. And even before the shell gets to you, there is a horizon. So you can have a horizon in a region of zero curvature. And that is completely true. Why? Because if you start running, the shell will collapse before you have exited. So horizons are really teleological. You need to know the whole history of space-time to define if there is a horizon or not. So for some reason, many people believe that they are not really physical.
What if someone applies a rocket and stops the acceleration of the
And then there is no horizon. And you need to know the whole history of space-time to say if I start running as fast as possible, if I will reach infinity or not. Of course, I need to read the whole geometry in order to answer that question.
Wait, wasn't there something that came up the other day where it depended on whether or not space-time was completely history dependent?
What was the discussion?
I don't remember.
Sounds familiar to me.
Yeah.
So we could start discussing these features for it because there is a lot of stuff here. So I just quickly summarize and gave to you the minimum things that you need to know to understand what I'm going to do from now on. So I need one more thing, which is Penrose diagram. black hole produced by gravitational collapse. Who has seen Penrose diagrams before? So you guys know what they are and how they are built?
I don't remember what they are, but I've seen them.
So because depending how much you know, I can give you more details or less. If you know everything, then I can be fast. But I know that some of you hasn't. So let me go fast.
Are those the ones with like the the multiple regions of space that look like this?
For some cases.
Then I've seen them.
But you know what they are, how they are built, what do they mean?
Mostly.
So the statement here is simple, is that we have all these diagrams and they look nice because they have a lot of colors, but I don't like they match because you choose as your axis coordinates. And coordinates are not physical. In fact, one of the problems of that made people to discuss for 40 years was precisely that coordinates are extremely dangerous and they have many artifacts which are not physical. So, you are using non-physical axes, and as a consequence, physical things like light cones are perfectly physical. You put up a light here, and whatever photons do, that is a light cone. No coordinates, nothing. They are just physical. Now geodesics. They are deformed in this plot, just because they are deformed because I wanted to have T and R perfectly straight. If our goal is to understand the physics of black hole geometry, to avoid any artifact, it would be much nicer have physical axes and let T and R have weird things. After all, T and R are not physical, so I don't care about them. So a Penrose diagram is a diagram in which light is always at 45 degrees. So light cones are always perfectly fine, at the expenses of having T and R doing weird things. But I don't care about T and R. My goal is to understand what we call the causal structure of the space-time. So how light propagates, what are the regions in which light cannot escape, etc. So to understand the global causal structure, it's much better to have light always at 45 degrees. So these Penrose, they are called conformal Penrose or Carter-Penrose diagrams. This is what I want to describe. So provide a compact and, in my opinion, clear way of representing the causal structure of the spacetime. And this is physics. Compare contrary to coordinates. So what I was planning to do was, just give you quite a schematic summary of the steps that you have to follow to build a Penrose diagram, and write explicitly the example, or more or less explicitly, the example of Minkowski spacetime, understand what happens in Minkowski spacetime, and then give you the solution for Schwarzschild. But the procedure is analog. So the motivation is clear, isn't it? Just have a spacetime in which the axes are physical. In particular, light, null geodesic is what we care about, because we care about what is the causal structure, which regions we can escape from, and at the expenses of having T and R doing whatever they want. I don't care about what T and R do. So I'm going to summarize for you the mathematical steps. And I will write an example of Minkowski spacetime, and to differentiate the theory from the example, what is general from what is particular, I will use blue. So whatever using blue makes reference only to Minkowski spacetime. So, a quite fast summary. I insist, if you really want to understand this in detail, you have to go to a book and spend some time. This is just a summary, quite brief summary, in fact. The first step is to write the metric using null coordinates. Why null coordinates? Because we want to pay attention in what light is doing. So what better than use coordinates which label different null rays. So in the Minkowski, you can write the Minkowski metric in null coordinates, and it is just dv du plus the angular part. The angular part is always there, is doing nothing. All the physics really happens in the TR plane, which is where the collapse happens. The angular part is an spectator that we are forced to write it. So this is the Minkowski metric in null coordinates, where in Minkowski u is just t minus r, so there is no r star in Minkowski. R star is only Schwarzschild. If you go to Schwarzschild and put mass equals 0, you get that r is equal to r star. And u and v is just the advanced null coordinate, t plus r, and you can see that both run from minus infinity to infinity. But minus infinity to infinity is, as you would agree, too large interval to write in a paper, because the whole space-time, and we will need a paper which is infinitely long. So what I'm going to do is to make a change of coordinates in which this becomes a finite interval. So I can just represent the whole space-time in a finite picture. So define new null coordinates. That take values in a finite interval. For that, I just need a function which transforms a finite interval in an infinite one, and there are many of them. For instance, the inverse tangent does that for us. The inverse tangent of v takes v that goes from minus infinity to infinity and gives you minus pi over 2 pi over 2. Tangent of u. These are my new coordinates. Just to have appropriate dimensions, let me divide by some arbitrary v naught and mu naught. So v naught, mu naught, arbitrary. For instance, choose them equal 1 in your favorite unit. So if you do that, you would see, regardless of the value of v naught and u naught, that v bar runs from minus pi over 2 to pi over 2. And, well, I forgot. This part is in blue. This is for Minkowski spacetime. I knew it was going to forget. And u bar also runs from pi over 2 minus pi over 2. So this box here is for me, for the example of Minkowski spacetime. can in fact write an Minkowski metric in those coordinates. The Minkowski metric in those coordinates are also like a flat metric. You know, in null coordinates, a flat metric is always du dv with a minus there. Plus sine u bar minus v bar squared. The angular part, but now we have a factor here, which is 4 over 1 minus 1 plus u squared, 1 minus v squared.
Is that u or u bar?
That's u and v. So if you want to write this factor, the whole factor, in terms of uv, and if this is just 2 times the cos of u bar, the sine of the cos of v bar. So because sometimes it's useful to have. So if you write u and v, you have to understand them as a function of u bar and v bar. And let me just call this factor, the whole factor, 1 over w or omega squared. I will use that definition later on, so keep that definition in mind. So the metric is 1 over omega squared times that. As you can see, this is general. So in the new coordinates, infinity is a finite coordinate distance. But as you can imagine, of course.
What is that omega?
Pardon?
Omega?
Omega is I have defined omega by that.
Oh, okay.
So just definition of omega. I will use it in a second. And the nice thing is that now, you know, infinity is a finite coordinate distance, but you can imagine the physical distance is still infinite, and you can see that because omega goes to 0 at infinity. So, you know, to physically really reach infinity, the physical distance is infinite. That physical distance, of course, is still infinity, and you can see that so that omega goes to 0 at infinity. This is why the physical distance becomes infinite. First step, construct a new auxiliary metric. So now we're going to construct a new metric, g mu nu tilde, which is different from my physical metric. So this one is not physical, it's something else I am building. I will tell you why is that interesting in a second. And I'm going to construct it by making or performing a conformal transformation. So, of course, the conformal transformation will depend on my particular space-time. So let me write it in blue because what I'm going to write is for Minkowski. That is analog. It's going to be omega squared times mu. Remember that omega depends on the point, so omega really is a function of the space-time point. So can you guess why I am doing that? So first of all, what after this comment here about the distances, what do I get with this?
Rescale the distance.
If I rescale the metric, I will kill this factor. So the distance between, Before I was saying that the coordinate distance between to infinity is finite, but this factor, because omega goes to 0, makes that the physical distance is really infinite. But if now I take this factor out, the physical distance to infinity will be finite. You know, in the new metric, the physical distance to infinity will be finite because the problematic factor is out. So what I get with this is taking the whole spacetime and bring it to a finite region that I can plot in my blackboard and see easily. So this is the goal. But second question, you may say very, very nice, but this is not my physical metric. So what? It's very nice that you can put this metric, this space-time in a finite piece of paper, but you know what I get with that if that is not the metric that I want to study the properties of. What's the answer? Penrose, Carter, and these people, they are not stupid. They are quite smart. So there must be a reason why this metric is still interesting for our goal. In fact, it's as interesting as the physical one for our goal. So just let me write what I just said. Now, infinity is at a finite physical distance. Physical distance with respect to the metric tilde. But now the question I was asking, why is this new metric, which has this nice property that, you know, the distance to infinity is really finite, is useful? Any guess?
You can still see the causal structure of the space-time because by factoring or just adding that factor to a metric doesn't necessarily change the sort of global character of whatever null surfaces may be.
Who agrees with that? Who disagrees? I agree. You know, because a conformal transformation means multiplying the metric by a positive factor, that will change the character of many things. In particular, you know, now time-like geodesics, sorry, not now. Time-like geodesics will be transformed in something else, which are not time-like geodesics. Spatial geodesics will be mapped to other curves, which are not geodesics anymore. But null geodesics will be always mapped to null geodesics. Can you guess why?
Because if ds is 0, ds is still 0.
Exactly. So null geodesic ds is 0, so you can multiply that, but wherever you want, ds will be 0. So that is the key stuff. So the two metrics share the same causal structure. That is the key one. So because a conformal transformation does not change the character of null geodesics. We'll change other things, but we don't care because so intuitively, if ds is 0, that implies that ds tilde, which is omega squared ds squared, will be 0. So therefore, G and G tilde share causal structure. Therefore, we can focus on the tilde one, which allow us to write everything in a compact piece of paper. One more step and we are done. the last step is trivial. So fourth step. Sorry. Extend the spacetime manifold because we have changed the metric, let's change also the spacetime manifold itself by including the boundaries. So I don't want to match, just include the boundary at infinity by including the boundaries. Because having the boundaries, will allow me to really have a compact. So what I want to do is to take my space-time. So I had the same manifold, but with the new metric. And now I want to extend the manifold. Just before, V was minus infinity, so minus pi over 2 open to pi over 2 open. Now what I want to extend it is to close. I want to include the boundaries.
Then it will stop being a manifold.
Huh?
It will stop being a manifold.
It's a manifold with boundary. And there are manifolds with boundary. So if you want my new, the new manifold, M tilde is just the previous M adding the boundaries at infinity. So I am just breaking the whole space-time to a finite picture and I'm closing it, adding the boundaries. Of course, the boundaries are not really part of the space-time because space-time doesn't have any boundary, but it's just the limit. And having the limit on our plots is very convenient to discuss where light is going to, where time-like geodesics are going to, etc. And now, the last step is just plot the space-time, the new space-time metric manifold with the new space-time metric using these new coordinates. So let me just do it. Okay. And let me just write the diagram for the Minkowski case, and that finishes the class today. So for Minkowski, so the example for Minkowski spacetime, suppressing angular, because another problem I have is that I don't know how to make plots in 4 dimensions. So let me suppress angular coordinates. So if you suppress angular coordinates, each point in the diagram, probably they cannot see this, is a true sphere. Sphere of radius, if I go to the matrix, radius sine u bar minus v bar. So then the Minkowski spacetime diagram.
Does that have a power after it?
No, because this is the radius square always.
Right, I just couldn't see what you had written on the board there.
No, there is no. That is the G.
Oh, okay.
So the Minkowski spacetime diagram is this one. Probably I won't have time to discuss everything in 10 minutes unless I go really fast. So perhaps this is a good point to stop, because otherwise I will have to repeat it next day. because it will take me some time to describe each point in this diagram, why it's like that, why it's not like that. So just, this is the Minkowski spacetime diagram. Light will go always, so this is the old r equals 0, so old r equals 0 surface. This is where the origin of radial coordinate it used to be. And
That should be zigzag, right?
no, in Minkowski there is no singularity,
Oh, yeah.
so everything is fine. So it's like this is a light that comes from infinity. Imagine that this point is the origin, so the light come to infinity. It's an incoming, now geodesic, so it follows v equal constant, so v is constant in all this line. It gets to the origin and goes through, so it becomes, it moves from being incoming to be outgoing. So what it's going to do is, and here it goes out, following a u constant trajectory. So this is incoming light. And so, as we discussed, this is the region where the destiny of light is. This is the region where the origin of light is. This is where particles with mass are originated. So any time-like geodesic will do something like this. This is where particles will die in the future. And I will describe different points next day, why they are what they are. And because if you understand this well, the Schwarzschild Penrose diagram is quite similar. So I think for me it's good to spend some time here, and we can dedicate the last 5 minutes to questions if you have questions.
I have a bit of a question. We're talking about in the Schwarzschild black hole, we have a point of infinite curvature in the center, which makes sense to me that it's a black hole. All light coming in is kind of doomed to stay inside it. But when skirting the details of what quantum gravity may be or describe, if it's instead just a area of very high curvature, it's still kind of possible for me to envision light coming in, going very high curvature, and then coming out. So I'm kind of curious if there are quantum gravity type effects, what that even means, or why being very high curvature still means it's not black in a sense.
The two things are related. Are unrelated. So
Mm.
one thing is the event horizon.
Yeah,
The event horizon is really far away from the singularity.
absolutely.
So, and I don't believe quantum gravity has anything to do for the event horizon.
So
Because,
the fact
as I said, in
that
this room, we may have an event horizon right now if a null shell will collapse next week. So and I don't think quantum gravity has to do with physics here, where the curvature is extremely small.
But I was kind of under the assumption that having a point of infinite curvature was intimately related with having a event horizon.
Not visible, they are unrelated. You can have an event horizon and having perfectly fine curvature inside.
Okay, but to have
I mean, theorems in GR tells you that, I mean,
they seem to go hand in hand.
they
unless-
say that you cannot have singularities without an event horizon. Or
Yeah.
this.
But
But
if
in
I
this-
had without quantum gravity, if I had very high curvature, then there
Right.
should be some null geodesic equality.
But the point is that eventually it's going to happen. I believe it's going to happen something like that.
Something like
Nobody knows when it's really going to happen. I'm just
Yeah.
my opinion. But the point is that by Hawking radiation, the black hole evaporates.
Mm.
So eventually, the light will be able to escape just because because the black hole has evaporated completely. So it is possible that a black hole forms. You get a region of very high curvature. A horizon is formed for a while. The black
So
hole
for
emits
a-
radiation, starts evaporating, and eventually it disappears. And some light that goes can go through.
So maybe it can be the case that light can come in through the event horizon and do something for a very long time, but then after everything's evaporated, like
It is
probably
possible.
collapse.
In fact, in order to recover information from the black hole, something similar must happen, in my opinion.
Does the Hawking effect emit light or does it emit other particles?
All the particles. Any particle is emitting the information.
So can light come in and other particles get emitted instead?
Say it again.
Does it violate like baryon number and lepton number and
No,
stuff
in
like
principle, because you always emit particle and antiparticle at the same rate. So,
But I mean, when things fall into the black hole, we don't think that the black hole retains a lepton number or a baryon number.
right, but
so-
that's a different question. That's even true classically.
So what it,
This non-Hare theorem tells you that black holes can only have mass, charge, and angular momentum, cannot have any other charge in principle, but maybe they have other charges. Like this new paper by Hawking and Strominger and these people, they say that there are other charges that could keep information of whether the black hole was formed by microwaves or by a star.
oh, so there's something about the evaporation process itself. that
Or
concerns-
even before, before the black hole settles down, there is raw radiation, the black holes, and after the black hole even is formed, it is possible that they have more quantum numbers that we haven't, that the ones established by the non-Hare theorem. So, but those are open questions. Nobody has proven that completely. Black holes are still challenging people in a very hard way. 40 years after Hawking. So don't expect all answers from me. Can give you my opinion. But.
Yeah.
Okay, so any other question? If not, let's see next Thursday.
So not this coming up Thursday,
Not this week.
and not the
Not
Tuesday.
Tuesday.
after the weekend. Okay.
I think it's 31st
Okay.
March.